Okay, thank you. And yeah, thanks for the chance to speak today. I'm also I'm happy to have the opportunity to talk in this series, especially at this time right now, because it coincides with the end of the Ancient Adhesives research project, which I've been involved in for about the last 4 years, and also marks about 10 years of research for myself on this topic. Um, So I'll begin the talk by introducing you to the topic as I was introduced to it, with what we knew about ancient adhesives about 10 years ago, and try to cover some of the important discoveries that have happened since then, along with a selection of my research and research that I've been involved with. Um, at the beginning, the first half, this should cover a bit of how and why questions, how these ancient adhesives were made, why those materials were used. That's a little bit of the reconstructing the adhesives. And then I'll try and cover a bit more about what that means for studying technological and cognitive complexity. Um, so here I was a little more than 10 years ago, sitting in an Introduction to Paleolithic Archaeology lecture as a young master's student at Leiden University, also here in the Netherlands. I had no idea that I was going to stay in Leiden. I had even less of an idea that this was going to make up a significant portion of my adult life studying these materials. My mind was pretty well blank on the subject. And then this image comes up on the slide. This is the oldest adhesive ever discovered. Okay, so what? Well, first of all, as a technology, adhesives are profoundly important. I don't think we really think about them very much because one of their whole purposes is to be invisible. Um, if you don't notice the glue holding something together, then it's doing its job. Adhesives should almost always be covered by the materials they're bonding. This is where sort of my second interest with adhesives come from, and maybe part of the reason why I was initially so intrigued by this oldest glue. I do a lot of woodworking. Um, and pretty much the aim of woodworking is to minimize the glue in your joint. You spend a bit of time choosing the best glue for the task, and then you spend a lot of time trying to make sure that all your joints fit together well and that nobody can see that glue in the end. So in any case, most of the time, you probably don't look at an object and think too much about the glue that was used in it, but adhesives are integral in just about everything that we make and use today. From shoes to smartphones to satellites, a great deal of time and energy goes into glue production, testing, development, and application. For example, just having a glue that can withstand all the abuse of a pair of shoes is actually really challenging. It needs to be flexible, soft, strong, stay together in a variety of conditions, in the hot, in the wet, cold. It also needs to be easy to apply, bond different materials together, some of which don't like glue very much, like rubber. Um, Adhesives for satellites have their own specific criteria, but in many cases, these problems that we face developing an adhesive today are the same problems that people faced hundreds of thousands of years ago, making adhesives for their stone tools. From a technological point of view, adhesives are also, from a technological evolution point of view, adhesives are also exceptional. Prior to adhesive technology, you have stone and wood implements, and these are mostly made in a reductive sequence. You start out with your tree branch or your lump of wood or a nodule of flint, and you remove everything that you don't want. With the exception of some heat treatment of lithics, the material property also doesn't change at all. The properties of the physical properties of the flint at the end are the same as they were at the start. You're just changing the shape by removing material. Adhesives are almost the exact opposite of this. You're collecting a small amount of adhesive, or even in some cases, unique different ingredients, and mixing them together in an additive process. Sometimes you're also transforming one material into another completely distinct and unique material. The birch bark that you see here in no way resembles at all the tar afterwards. You couldn't predict by looking at the tar that it came from something that looked like the birch bark. And then you can shape, mold it, melt it, reshape it, join multiple different things together, also in an additive process. So very different process than simply reducing a piece of stone into a stone tool. Along those lines, after gluing these objects together, it greatly improves the efficiency of the tool. If you try swinging a hammer or using a steak knife without a handle, you'll see that the adhesive in this case is very useful. And after that, they're also used to waterproof containers and then boats. So this allows for transporting water and, of course, transporting people over water, all starting with this humble birch bark tar. In a book entitled The Dawn of the Metal Age, the author describes transformative metallurgy as a technological paradigm shift, something that fundamentally alters the way humans understood and interacted with the materials of their environment. I would say that adhesives are really the first of this paradigm shift, since they're transformable in the same way as metal. That metallurgy is really just more of a follow-up about 200,000 years later. Okay, so now we know at least in part why, at least I was interested in the first adhesives. There's much more that makes them worth studying, but this is enough to get going. Back to this object here. So it was published in 2006. This is a lump of birch bark tar wrapped around a flint flake. The tar is on the bottom half here. It comes from a fossil-bearing bed, which predates marine isotope stage 6. So the authors argue that it's at a minimum of 191,000 years old. It could be older. It also comes from central Italy, which means that it's pretty well unequivocally associated with Neanderthals. So at this time, we didn't know too much more about birch bark tar. In 2001, so predating that a little bit, there was another publication about another discovery of birch bark tar. Again, it was quite a sizable lump of birch tar. This one was from Germany and dated to at least 40,000 years old. In this publication, the authors made a statement based on the chemistry about the production of the birch bark tar. They referred to this in their title, High Tech in the Middle Paleolithic. They claimed that because certain chemical compounds are found when they analyzed the material, that it must have been heated to within a very narrow temperature range to produce the tar. They suggest that it needed to be heated between 340 and 400 degrees Celsius. This precise control of fire was then argued to prove Neanderthals' technological prowess, especially regarding pyrotechnology. In part, this is true, but it's also a bit of an oversimplification, which we'll see more of later, because we didn't really understand how the tar was being made, whether this 340 to 400 degree range is really required or not. Turns out it actually doesn't need to be heated within that narrow temperature range. It can be produced above or below. But this particular piece was heated in that range. So in any case, for around 2006 to about 2010, there's pretty much these two publications on two major findings of birch bark tar. They're showing that, for one thing, it's a high-tech material, requires complex pyrotechnology, and it's also the oldest such material or technology in the world, predating anything by anatomically modern humans. But we don't know a whole lot more than that. So two questions in my mind at the time are, first of all, how did they do it? How were Neanderthals making this birch bark tar? We really didn't understand the process. How to do it without ceramics, basically, ceramics or metal containers. And second of all, why did they do it? Why did they want to use birch bark tar as an adhesive rather than some other material? Other people had the same thoughts. There were a couple of publications and experiments attempting to reproduce birch bark tar using only Paleolithic technology. These were promising. Many of my experiments later was influenced heavily by these earlier attempts, but they tended to produce charred and tarry bark or small amounts of tar, like the residue on these thermocouples, as you can see here. And we wanted more tar. So together with some colleagues, Diedrich Palmstra, and at the time my PhD supervisor, Geeske Langejans, in 2016 and 2017, during my PhD, I set out to make quantities of tar that are comparable to what is found in the archaeological record. We know that these lumps, like you saw in the previous picture, they're quite sizable amounts encasing this flint flake. So these are some early pictures of our experiments. I can assure you that not all of the field experiments we did here in the Netherlands are under blue skies and sun. There's a reason why we're working under this sheltered area in the top left. We tended to do our experiments in the middle of winter. I'm not sure why, just the way the timing worked out. And it wasn't always sunshine like this. But in any case, so tar is generally formed during the destructive distillation or the thermal degradation of any organic material. With woody material, it's a pyrolysis product of lignin, cellulose, and hemicellulose. This makes it a complex mixture of compounds, mainly composed of aromatic hydrocarbons. So it's essentially a crude bio oil. And due to the extractive content in birch bark, this material in particular is well suited to making tar adhesives. So this may be part of the reason why the birch bark was used as a material to make tar rather than something else. There's a number of other reasons as well, but the idea here was to add heat from a fire, but to limit the oxygen so that the tar would form, but it wouldn't combust. That's why we're covering it in earth here in this one scenario. So in one single attempt of making tar, in our best attempt anyway, we were able to produce quantities that are comparable or larger to those known from the Paleolithic archaeological record. On the left, you see the lump from Germany, and on the right is the best amount we made in a single attempt. We published three methods, three potential techniques that Neanderthals could have been using to make tar, but discussed that there's probably many more ways of making tar as well. The next few slides, I'll explain some of the sort of most probable or efficient methods of making tar that we've found and that other people have found. The first of which was discovered a few years after we made that publication by another research group. They called this the condensation technique. While we were busy trying to exclude oxygen to increase the tar yield, they found out that by simply burning small pieces of birch bark right next to a vertical stone surface, enough tar would actually condense on that stone, and you could scrape it off and collect it. In these pictures, what you see in the bottom right, this little ball of tar, is probably the result of about 30 or 40 minutes of burning and scraping to collect these tiny bits of tar. So it's a fairly slow process, but you can immediately recognize that there's something there on that stone that you can see, and you can collect it and feel the stickiness between your fingers. One of the methods that we came up with, we refer to imaginatively as the pit roll method. This is because it starts with a roll of bark stuffed in a pit. After that, you pile some hot embers or some burning logs over top of it. And this is a pretty small roll, about maybe 10 centimeters tall and 5 to 10 centimeters in diameter. And after you pile these embers on it with a small piece of birch bark at the bottom of the pit, enough tar forms inside the roll that it drips down through the roll and collects in this little cup at the bottom of the pit. So here you can make a little bit more tar by just kind of putting it in the ground, preparing it, and then leaving it alone for a while. Taking that kind of technique to an extreme, this is the largest and the longest process, but it's also the most efficient in terms of yield per birch bark used. We refer to this as the raised structure. Maybe we should have spent a bit more time thinking about how to call these different techniques. But in this case, there's an earthen or mud oven-like structure that's built up above the birch bark, hence the raised structure. The birch bark inside this structure is placed over a mesh of sticks or twigs, and beneath that is a pit in the ground with a larger birch bark cup. Then you light a fire all the way around this, let it burn for several hours, and the tar is formed inside the oven, which is excluding all the oxygen, and drips down into the cup below, and you get quite a large yield of tar from that technique. But it's something that takes quite a lot of planning and preparation, and then you can kind of leave it alone as the fire burns for several hours. So very different technique to the first condensation process. I'll get into a little bit later what that means, how the techniques were different, what that means for the behavior behind the techniques. Then around this time, another lump of birch bark tar was found. So now there's basically 3 sites that have these large lumps of tar. Still not a lot, but we added 50% more tar knowledge with this one discovery. It was found by an amateur archaeologist combing the beach at the Zandmotor here in the Netherlands. What this is, if you haven't been, is an area of beach in the Netherlands where the sand has been dredged up from just offshore in the North Sea and piled at one end of the beach. The current distributes this sand up the coastline, which replenishes the beach and prevents erosion of the coastline, helping to keep the Netherlands above water. That's great. An added benefit is if you're really lucky, you can find something like this by just walking along the beach. It was radiocarbon dated to be about 50,000 years ago, towards the limit of what could be detected with radiocarbon. And again, it was chemically analyzed and identified to be birch bark tar. We hypothesized, based primarily on the yield, that it was a large amount of tar, and we knew from the previous experiments which methods were more efficient than others, and that the environment at the time this was made, that there was very little woody material around. So we hypothesized that Neanderthals were likely using one of the more complex methods of producing tar. Also, the fact that they were using such a large amount of tar on a flake that didn't really seem very special in any way would indicate that they had a good grasp of this tar-making technology, that they were prepared to use it on any old flake. Nonetheless, there was still some debate about whether or not it was really complex or not. We'll talk more about that later. Okay, so that was digressing a little bit. We've got an idea now about how the tar was made. Now we can ask a little bit about why was it being made? Why would you use birch bark tar, which has this time-intensive or costly production process, when there are readily available alternatives in nature, such as this pine resin? So to do some further tests, I selected pine resin as the most likely alternative to birch bark tar as an adhesive. Pine trees are about as abundant as birch and occurred in many of the same times and environments throughout the Pleistocene. But unlike birch tar that needs to be manufactured, pine resin is just exuded from the tree naturally, and you can immediately recognize that it's a sticky substance. It's also known to have been used as an adhesive from later time periods, so it does function as an adhesive. But yet still, all the earliest adhesives we're finding from Neanderthals are birch bark tar. So why could that be? To test for this and to try to understand what makes a particularly good adhesive for hafting stone tools, we have to look at a few different criteria. And then what I do is I tested a comparison of birch bark tar and pine resin to see which one is better at these criteria. So first of all, the adhesive should be available in the environment. It needs to be something obtainable. The more readily available, the better. It should have good gap-filling properties. So unlike with fine furniture making, with stone tools, there's often a very big gap between the stone tool and the wooden handle. And the adhesive needs to be able to fill up this space. For this reason, hot melt adhesives, so something that you melt to apply, are usually used for gap filling, since they don't shrink very much when they dry. If you have an adhesive that dries by evaporation, it's going to shrink up a lot as it dries, and if you have a big gap, it's going to break away and leave a void in that gap, and it won't be very strong. So another criteria is the wetting and the flow characteristics. This goes along with point 2 and 3, that an adhesive needs to be liquid enough to wet the surface in order for a chemical bond to form, but not so liquid that it just drips out of the joint before it has had time to set. 5 is probably the most obvious. It has to be strong enough at the temperatures that it's used in. If it's used outside year-round for demanding tasks, it should perform well at those temperatures. Doesn't matter how well it performs at -50 or like adhesive for a satellite. In this case, looking at a range from maybe 0 to 25 degrees or something. And finally, it should have a limited thermal degradation during application. That it's being applied by heat, so and the only kind of source of heat is an open fire in this case. If the adhesive is negatively affected by too much heat, it's going to be very difficult to apply without destroying the adhesive. So highly volatile materials, for example, are not very well suited to this because you warm it up and it's going to either combust or break down. I realized I missed a point. That's number 3, which is the melting and working temperature. And this is because it's a hot melt, it needs to be melted down, but also applied by hand. So it shouldn't get too hot. There's not a hot glue gun in the Paleolithic to apply. You have to actually stick it on with your fingers. So then to test these criteria, I looked at rheology to measure the flow of the adhesive over a range of temperatures, surface hardness of the material before and after heating to different amounts to show how the hardness, its ability to resist deformation, changed as a function of time, and also its thermal degradation while being heated in thermal gravimetric analysis. I'll quickly skim through these results, but this one, it looks like a mess, but I'll give you a quick rundown with a few key areas highlighted. So when we're looking for of what we're looking for with a natural hot melt adhesive, first of all, when the loss modulus, that's basically the liquid portion of the adhesive, is greater than the storage modulus, which is the solid portion of the adhesive, that means that the adhesive is open. It can then wet the substrate. That's when the chemical bond of the adhesive takes place. It's essentially when the liquid portion of the material dominates. In this temperature, for birch bark tar, it's a little bit over 40 degrees. So below this temperature, and it's not going to be a sticky mess. The resin, the pure resin, this happens at about 10 degrees. So anything above 10 degrees and the resin is already sticking to your fingers and being very difficult to apply and to use. The birch bark tar is not like that below 40. The change happens at about 40 degrees, which also means that at 40, 50, or 60 degrees, the adhesive bonds really well and is liquid enough to bond to the materials, but that's still cool enough that you can handle it and press it and shape it. It's not happening at 100 or 200 degrees. Second of all, in an adhesive system, a higher storage modulus, the elastic portion, G prime, usually indicates improved impact and peel properties. So these are good. You want impact and peel resistance. Implements like spears or axes, they need to resist impact forces, and things like scrapers need to resist peel forces as the adhesive wants to get peeled out of the object that's on it. For birch bark tar, again, this is higher than the other two adhesives across the range of temperatures from about 0 to 25 that we tested here. And lastly, when the elastic portion of the material is dominant, so when the adhesive is set, a lower tan delta value, or this is a ratio between G prime and G double prime, generally indicates higher cohesive strength, so the ability for the adhesive to stay together within itself. And again, this is good. You want a high cohesive strength in an adhesive. And for birch bark tar, this is better than the other two mixtures. This is what it's being compared to here is a pure resin and also a resin and beeswax mixture, because the pure resin on its own is really not very good. And there's some evidence that it was mixed with beeswax to try and improve that. So that's what we're comparing here is tar with the resin and beeswax. To give a bit of a practical idea, put that into perspective, some modern general purpose hot melt adhesives, they generally have a storage modulus of about, at 25 degrees, of between 50 and 500 megapascals. The birch bark tar here is about 150 megapascals, so it's within that range. And they usually have a tan delta value at the same temperature of about 0.1 and 0.3. With the birch bark tar at a little bit cooler, it's got a tan delta value of about 0.3. So it's close. It's approaching the quality of some general purpose hot melt adhesives that we use today. To look at the thermal degradation of the material after heating it, The hardness measurements were taken at 5 minute intervals of heating the material. The tar in the black here shows very little change after heating it for up to 40 minutes. The pure resin, on the other hand, changes very quickly with heat. And after just 15 minutes, it becomes so brittle that you can't take the measurement anymore. It just shatters and breaks. The resin in beeswax is a bit closer to tar, but still has a little bit more variation. Likewise, rheology measurements before and after heating the tar, which is what you see in the dotted black line versus the solid black line. There's very little change with the tar before and after heating, whereas the red and blue are showing the resin and the beeswax mixtures, and they vary quite a lot. After heating it, the performance changes quite a bit, so they're much more susceptible to being overheated during production and application. This is also confirmed by the thermogravimetric analysis. In this case, tar is virtually unchanged until about 250 to 275 degrees. So you could heat it anywhere in that range and not a whole lot is going to happen to it. With pure resin, on the other hand, after about 100 degrees, it starts to change quite significantly. This is beginning with the turpentine fraction evaporating and it becomes more brittle. And then at around 150 to 200 degrees, the rosin acids start to break down and it again becomes degraded and not such a good adhesive. So you can see that the tar is really basically outperforms resin in most of the cases. So to get back here to the criteria, points 1 and points 2 are both satisfied for both of the adhesives. They're both available in the environment about equally. They both are hot melts and have good gap filling properties. Point 3 is given to birch bark tar because the working temperature is high enough so as not to be too soft during regular use, but low enough not to burn you when you apply it. Point 4 also goes to birch bark tar. It remains firm so as not to flow out of the joint. Yes, because of the low open temperatures, resin, on the other hand, is very tactile at low temperatures, which makes manipulating it and applying it very difficult. Point 5 also goes to birch bark tar. It's basically got better performance. It's stronger across the uses and temperature ranges. And point 6, also taken by birch bark tar, it shows very little change after prolonged exposure to high temperatures. This is also useful in environments like where that sand motor tar was discovered. If the bark is fairly scarce in the environment, then you want a material that you can perhaps reuse. And birch bark tar could be reused many times without any negative effect. Pine resin, on the other hand, after heating it again a second time or a third time, becomes extremely brittle and difficult to use. So to wrap up this segment of why use birch bark tar, what we see is that birch tar clearly outperforms the other kind of most obvious natural adhesive in pretty much every criteria. It even approaches the properties consistent with some modern general purpose hot melt adhesives. The fact that Neanderthals were using this material spanning 150,000 years and ranging from Italy to the North Sea, despite the initial production being costly, indicates that they probably had a pretty extensive understanding of the qualities and the materials in their environment, qualities of the birch bark tar, what they were after, and that they probably chose to use this material because of its advantageous properties. Now, moving on from the birch bark tar and going to this what question of what it might mean for studying human evolution, parallel to the research on Neanderthal birch bark tar, which was really focused on how it was being made and why it was being used. Research in Southern Africa on compound adhesives was already moving forward into discussing it as a proxy for recognizing complex cognition. On these adhesives, these compound adhesives that were a mixture of 2 or more ingredients, usually a hematite-containing pigment, like red ochre, and then a gum or a resin. So these South African adhesives are typically not quite as old as birch bark tar, The oldest of these is around 60 to 70,000 years old. It still puts them firmly in the Middle Stone Age and contemporaneous with some of the other birch bark tar finds. With these compound adhesives, the questions of how they were doing it was not such a mystery. They were mixing together these ingredients. It can also be why they were mixing them can also be explained because of performance. Mineral fillers such as red ochre tend to improve the quality, the workability, the strength of these resin-based adhesives. The real question being addressed here, and what we're getting to with the tar, is what does it mean for the human behavior and evolution behind the production of these adhesives? So this research from Lynn Wadley linked compound adhesive production with cognitive complexity. This is a very kind of important finding for me, research paper for me, and something that we'll discuss a little bit more and I'll get back to later. But basically during her field experiments, so she went out and tried to replicate some of these Stone Age adhesives as well. And she recognized as she was doing this, the need to utilize a number of different cognitive processes, such as mental time travel, forward planning, abstraction, innovation, task switching. To make a good compound adhesive, you need to know which ingredients to mix in which proportions. You need to prepare them in advance, collect them from different places, plan ahead thus, balance, and when you actually get to it, balance and rotate your tool, the consistency of the adhesive, the heat of the fire, all of these things at the same time. So that's part of the reason why adhesives were seen as this a nice behavioral proxy for something like complex cognition. Some of these processes with the compound adhesives are very similar to making birch bark tar and to applying birch bark tar, but some are quite different. So direct comparisons between Neanderthals and anatomically modern humans in this regard was not always very straightforward. And then fairly recently, a couple of years ago, there was another paper by some colleagues at Tübingen University, that suggested that Middle Stone Age humans were also manufacturing tar as an adhesive, not just using resin or gum. Here the authors stated that podocarpus tar was preferred to many readily available exudates. This documents a high degree of innovative potential and the understanding of desirable material properties. Sounds an awful lot like the selection and use of birch bark tar by Neanderthals. And that podocarpus tar is therefore an excellent proxy for recognizing complex cognition. So good news for Neanderthals, right? They were, after all, making tar much earlier. But still, not everybody was convinced or accepted that it was the same, and this led a few people feeling a little confused. There was a series of research publications that bounced back and forth. Neanderthal tar was complex, Neanderthal tar was not complex, Middle Stone Age tar was complex, and on it went. But for all of this discussion, there were some meaningful contributions, but there was very little about what was the complexity. Further to that, there were almost no actual measurements. So how could we really compare these technologies or measure how it was changing, either across space or across time? Of course, there exist a number of ways of measuring the complexity of technologies. The number of components was used for birch bark tar, and this can be very similar to techno units, which have been around for a long time. You can also look at the number of steps in a process, counting these steps. But this is still missing a kind of fundamental behavior aspect to the complexity, which is how complicated is each step or how difficult each step is to make. A lot of that comes from the interpretation of the experimenter. This is the other way that adhesive complexity has been discussed. If an experimenter found one technique to be particularly hard to complete, it was deemed complex. If another was very simple, then that technique was less complex or required less cognition to make. The experimenter might feel that they're having a hard time switching tasks or preparing multiple steps in advance. Therefore, that method would be assumed to require cognitive traits such as forward planning or task switching. But again, this isn't being measured. It's a subjective view. So comparisons between experimenters is difficult. And of course, when looking at any technology like this with experimental archaeology, we can't ignore the fact that we are not the same now as we were back then. 200,000 years ago, especially as you're getting so far back in time. As good as I like to think that I am at making tar, I'd probably be laughed at by a group of Neanderthals, and I won't deny that. So this is exactly where the Ancient Adhesives project comes in. This is the project I've been involved with the last 4 years that's just wrapped up, led by Kozowyk. The aim here was to create a computational method to study technological complexity. This is to move from the qualitative experiments to a quantitative analysis and to measure production complexity in a manner that's more meaningful to look at cognition. The first step in this case, studying birch bark tar, is to identify some of these cognitive traits that can be considered signs of cognitive complexity, and then to find a way that we can measure them in the production of birch bark tar. Going back to Lynn Watley's research, she defines cognitive complexity through Stone Age technologies as the capacity for abstract thought, analogical reasoning, cognitive fluidity, innovative thought, complex goal-directed actions, flexibility in problem solving, multitasking, task switching, response inhibition, and planning over long distances of time. Now, we can't measure all of these things, but we were able to identify 3 criteria that could be measured in a quantitative way. So what are these cognitive requirements for making tar? One is to retain multiple pieces of information at the same time, or multitasking. The second is to avoid errors in the production process. This is also connected with response inhibition. And the third is to understand the process before starting to make tar, which is also connected with abstraction and understanding. To quantify these criteria, we applied Petri nets to model different tar production methods. Petri nets allow us to measure these requirements through a number of pre-existing metrics that are basically designed to calculate the complexity of a Petri net model. A lot of this work was done by Sebastian, that you see here, recording us making tar. He's the modeling guru, so I'll do my best to explain the techniques, but I'd be also happy to redirect you to him after if there's further questions about it. First of all, what is a Petri net? Well, it's a graphical and a mathematical modeling framework. It's used in many things, but particularly in business analytics for mapping and measuring information or business processes. Petri net has 4 elements: places, which symbolize conditions or resources; transitions, which represent events; arcs, to mark the flow of the process; and tokens, to symbolize the state or the condition of a resource. So Sebastian watched us making tar in these 3 different techniques, ranging across kind of what were considered to be different levels of complexity. The first is the condensation method, the second is the pit roll method, and the third was the raised structure technique. And then we applied 3 existing metrics that are used for measuring the complexity. These come from the literature, and I'll go through these 3 different methods and how they tie into those criteria that I listed earlier for what's required to make tar. The first is the density metric. This measures the interconnectedness between events and resources. It can be related, therefore, to requirements of simultaneous information processing. So this is our proxy for retaining multiple pieces of information at the same time, like when you have to listen to 2 conversations at once. The density metric is calculated. It's simply the ratio of the number of existing arcs in the Petri net to the maximum number of possible arcs. So in this case, we have 10 existing arcs, or the arrows, but there's 48 possible arcs. So 10 over 48 is a little more than 0.2. If the process were to have 6 more arcs, the Petri net would get more dense. The new calculation would be 16 divided by 48 possible arcs, or 0.3. The second metric is the extended cyclomatic metric. This concerns the likelihood of errors throughout the process and the potential need for planning and inhibition control to try and limit these. Choices are indicated the number of choices are used as a proxy for avoiding errors. And choices are indicated with different paths throughout the graphs. The wrong choice can end up costing time and resources, like when you accidentally click update and restart on your computer. To calculate the extended cyclomatic metric, first, the Petri net is used to create a reachability graph. In this case, the square boxes here are all the same Petri net, and you see the token, the little black dot in the middle, moving through the Petri net. So in the initial phase A, which corresponds with the top circle on the reachability graph on the right, you have only P1 has a token. So in the reachability graph, there's a 1 in the place of P1, and then a 0 for all of the other places. In letter B, when T1 fires, the token can move to both P2 and P3. So in B, you have a 0 because there's nothing in P1, a 1 for P2, a 1 in P3, and then a 0, 0, 0 for P4, 5, and 6. This moves on in the next stage. T2 and T3 can occur in any order, including in parallel, which produces tokens in both P4 and P5 for C and D. This is why the reachability graph splits. And then T4 results in a token at P6, which is the final reachable state. So this is how the reachability graph is calculated from a Petri net. From there, there's a simple formula to give you the extended cyclomatic metric, and this is that the extended cyclomatic metric equals the number of edges in the reachability graph, subtract the number of vertices in the reachability graph, plus the number of strongly connected components, which are what's shown in the large red circle here. In this case, you have 11 edges, subtract 8 vertices, plus 4 strongly connected components, and your final your final extended cyclomatic metric score is a 7 in this example. And finally, the last metric for measuring the complexity of these Petri nets is the structuredness metric. This relates to the effort to understand abstract information about the materials, the product template, or the process itself, and thus relates to learning the process. So it serves as a proxy for the level of understanding required to complete a process. Ironically, it's also been the one that's the hardest for me to understand and to explain. But generally, a process with more relations and elements are harder to understand. The metric itself is calculated by an algorithm which searches the Petri net for 7 different components. Each component is then weighed following the order that you see on this figure. And the algorithm searches, weighs, and folds each component until a single transition remains. Then the weight of that last transition represents the weight of all the identified components, and this gives you the final score for this method. So, with all that out of the way, the results are much more straightforward and much more interesting, anyway, for me. These are the 3 different techniques and the 3 different complexity metrics. In the top, you have the density metric, showing the density score for the condensation, the pit roll, and the raised structure. In this case, the condensation method scores the highest for the density metric, but it's also the lowest for the other 2 metrics, meaning it has the highest need for simultaneous information processing, but the lowest need for planning ahead and understanding abstract information. The raised structure, on the other hand, scores the lowest for the density metric, but the highest for the other 2 metrics, making it the one that requires the most task switching and inhibition control and is also the most difficult to learn and comprehend. The pit roll falls in the middle for both of these, falls in the middle of both of these methods for all of the metrics. So you could see the condensation, the 2 extremes, the condensation and the raised structure as 2 different cognitive strategies to solving the same problem of making tar. One relies more on intense processing of information at the same time, like this bus driver, and the other relies on a greater ability to learn and to comprehend the process in advance, also to plan and prepare. Now, at the time that we did this modeling paper, it wasn't known at all which method was being used. We were assuming that based on the quantities being produced, as I showed earlier, that probably they had a very good grasp of the tar production and the technology and were able to use some of these more longer processes like the pit roll and the raised structure. But then shortly after that, there was another paper published modeling different tar production techniques, shortly after the research paper modeling different tar production techniques was finished, this new finding was published, suggesting that one of the archaeological tars made in the Middle Paleolithic from the German side so that's something like the ray structure or the pit roll. It's not easy to distinguish the two. And keep in mind, this is also comparing 50,000-year-old tar with something that's made kind of yesterday in an experiment. So there may be some variation when the tar ages. But in any case, they're arguing that it was made underground in something like the pit roll or the ray structure. Perhaps a condensation technique was an initial discovery, something that you can kind of find accidentally if you're burning bark beside a stone. But then later, in this case, Neanderthals likely innovated more efficient and better solutions. Solutions that produced more tar, but that relied on more planning, or maybe even communication to explain and to teach and to pass on the techniques. Whichever method was used to make tar, there's one main takeaway here. It used to be a clear case of apples and oranges when looking at Neanderthals and modern humans. Obviously, it's not so distinct anymore. Most people will be well aware of that. Of course, this view has been changing for some time. Adhesives are only one of the areas where we are finding similarities. We did, after all, have offspring together. But for nearly 20 years, archaeologists have been fairly confident that adhesive production among Middle Stone Age humans is a clear sign of complex cognition and modern-like thinking capacities. But there's remained skepticism that this is also the case for Neanderthals. Now, however, Neanderthal adhesive technology is very easily comparable to anything made during the Middle Stone Age by Homo sapiens. And finally, obviously, there's no such thing as modern behavior or complex cognition. These are sliding scales. They changed over thousands of years. Neanderthals certainly exhibited some of these traits associated with those terms in exactly the same way as Homo sapiens did, but at least 100,000 years earlier. I'll end it with that. Thank you very much for your attention, and I would also like to thank the Ancient Adhesives team, in particular, Alessandro, Sebastian, and Keiska, and yes, Phoebe for inviting me, and all of you for your attention.
Thank you very much. That was absolutely fab.
Would you like me to keep sharing the screen or to?
Yeah, that's what I was just about to say, actually. Do you want to unshare it and then we can just look at people's names?
Yes.
So if anybody has a question, we have about 10 minutes or so. So yeah, if you want to raise your hand or put the question in the chat, I will read it out. But we have a hand raised from Walter. If you would like to unmute, go ahead.
Sure. Thank you for calling on me. It was a very fascinating lecture. I like the way you combine stone tools and mathematical models and cognitive advancement. So the question that I have is if in sites where these tools were found, was there any evidence of sedentary culture, such as even shallow vases or urns or mortars and pestles?
No, nothing like that.
Nothing like that?
No. So unfortunately, with the birch bark tar, two of the finds have been, well, they were the Zan motor tar is completely out of context. It was dredged up from the North Sea, so we know nothing about the site that it came from, only the date. The Italian find was from a riverbed, I believe, and the Koningsau find from Germany does come from a very well-documented find. There are, I believe, hearth features, but nothing, certainly nothing like mortar and pestles or containers or vessels, nothing like that. And from the South African adhesive finds, there's a few where they find shells with some pigment, maybe adhesive or paint mixtures. It's not clear whether that's used for the adhesive production or for mixing pigments for some other purpose as well. So there's not a lot of evidence connecting or from these sites for any kind of thing like that. They're really the tar objects are really kind of in isolation. We don't find any kind of production traces. So far, the only evidence for kind of reconstructing the production method is the chemical signatures that's in the tar itself.
Interesting. All right, thank you.
Thanks, Walter. I had a question actually. Some of the younger examples, do you think that with Homo sapiens, the date of Homo sapiens in Europe being pushed back and back in recent years, is there any risk of a reassessment of these younger examples being part of Homo sapien cultures rather than Neanderthals?
That's not a bad question. I would think, I mean, it depends how extreme the date gets pushed back in the future. You never know. But for example, the one from the Netherlands is at least 50,000 years old, from Northern Europe as well. So it's not in an area where you have very early Homo sapiens arriving in Europe. It would take probably some more time or some a very fascinating, new, groundbreaking discovery of Homo sapien evidence in Northern Europe that far back to push it to be evidence of Homo sapiens. Something like the Neanderthal, or sorry, the Campitello quarry tar from Italy that's around 200,000 years old. That's going to be pretty hard, I think, to ever argue that it was from early Homo sapiens. But certainly, I mean, it's interesting that the new suggestion that Homo sapiens were making tar adhesives from a different material in southern Africa is interesting. Before it seemed as though Neanderthals were making the tar, and then maybe Homo sapiens came to Europe and then started making birch tar as well. It would be interesting if we found other tar adhesives kind of between southern Africa and Central Europe, and see that maybe they brought a different tar technology with them, or maybe it was forgotten. I think it's also possible, based on the different ways that you can produce tar, it's not unlikely that as the environment changed, maybe the technology of producing tar was forgotten and then re-emerged again, was rediscovered later. Perhaps this explains why it seems to have lasted 150,000 years, but we only have a few examples. Most likely we'll get more, and it's a preservation issue, but I'm not sure if that probably went off topic of your question a little bit.
No, that makes, I can follow the reasoning. Yeah, thanks. We'll give it a minute or so to see if there's anything put in the chats. Got a couple of messages saying thank you for a fascinating talk, and a couple of people saying they're having to leave for other meetings.
Yeah, I ran a little long, sorry about that.
No, it's fine. I can't see any more questions coming in, and we have gone kind of neatly up to the 2:00 mark.
Okay.
So if that sounds okay with you, thank you again for such a wonderful talk. I really enjoyed it. And yeah, it was really nice to see the evolution of your research as well.
Thank you. And yeah, thanks for the invitation. It was really great. I enjoyed giving the talks. Thanks again.
Thank you. Bye.
Bye.